Susan, that is it 1 hour?
We have 1 hour, yes.
Okay, all right. So it'd be the fastest, quickest introduction to the Bayesian paradigm technique in the software. So there's 3 parts in here. Roughly, I don't know, 20 minutes each. Tell you what the paradigm is about, and focused on some of the popular techniques to estimate the Bayesian posterior distribution. It's an estimation problem, and then I overview some of the software packages to claim a conflict of possible interest. And I am a software developer. I do PROC MCMC, so PROC MCMC is one of the software packages that I'll cover in here. Okay, let's just start. So the Bayesian paradigm is about estimating something, and often we say the estimation is, from a statistical term, is the parameter of inferential interest. And now the parameter can be regression, hazard ratio, missing data, or anything that you wish to learn, and that's what we want to know. Okay, so in a Bayesian mindset, we essentially start from this thing called sampling distribution. We know that we observe data X, and it's being generated, it's controlled by some underlying unknown parameter mechanism, and we want to flip them. We want to say something about the parameter given the data. This switch, this is called switch. People also refer to as inverse probability. From data given the parameter on top, can people actually see my cursor?
Yes, we can see your
Okay.
little arrow, little hand.
Okay, all right. And then switch to parameter given posterior is the essence of Bayesian paradigm. This is it. This is it. So now you say, are we talking about likelihood or posterior? Or are we simply switching the likelihood function with the posterior distribution? We are using the same thing, just called this function as a likelihood function, a sampling distribution, and the same thing called the posterior. And this is a picture that you can look at the same thing from 2 different angles. It is almost just like that, boils down to it. And the switch is carried out by Bayes theorem. And surprisingly, the whole Bayesian paradigm is based on this, that in order to switch from data given parameter to parameter given data, you need to have a prior distribution. And you have to deal with the amount of assumption that come with it. And there are certainly some caveats that come with it. So the formal Bayes theorem is this. The posterior is, you know, the people probably already know what this is, and I will go in detail of it. And there's some requirement. The caveat is that this distribution is actually a distribution, has to be a proper distribution. So typically we start as a sampling distribution. The data generating mechanism of parameter infer on the X, that's a proper distribution or normal likelihood. It doesn't put any requirement on this function need to be a proper distribution with respect to theta, and the Bayes theorem requires that. And the second caveat is you must using a prior distribution. That is a must, and that sometimes is an issue to a lot of people. This is the same thing. It cannot be a constant all the time because for the reason I described, the posterior is not guaranteed to be proper by with a flat prior. Okay. So to contrast the Bayesian paradigm, to summarize the Bayesian paradigm, this is from a book by Larry Wasserman, all about statistics. So the Bayesian foundation describes probability as a degree of belief. It has nothing to do with limiting frequency. It is very subjective. And again, because of that, the Bayes theorem, it follows that the parameters themselves cannot be determined exactly. They are random variable. That's why they have a distribution. And all your inference about theta is based on the probability distribution of that parameter. So that accounts, that's the only thing that you would care about. On the other side, there is a different approach, is what many people are familiar with, is a frequentist classical approach, where the probability are believed to be relative frequency. How long you run your experiment, how long you throw your dice, and then the parameter themselves is fixed, and the statistical procedure should be designed to have these well-defined long-run frequency, such as a confidence interval. By long-run frequency, it reflects the very basic assumption that probability refers to a limiting frequency. And since parameters themselves are fixed, statistics, when you practice it and do it, is really on data. But on the other side, Bayesian paradigm is focused on parameter, not on the data. So just this a simple diagram of how you see Bayesian versus frequentist. You collect your data, you have xn data, that's what you have. You might be able to see more and more data that's represented by the red. There is this single line right here. On the left-hand side, Bayesian inference is based on what you have observed. It doesn't make any assumption on what you will see in the future. And just like, given what I have, this is the most information I can say about my parameter. So I'm addressing the parameter inference directly. On the other hand, the frequentist domain assumes that the future data, there'll be infinite more future data that you will see. And then in asymptotic, we find out what would happen. So the statistics is on the data and using that to infer on what would happen if such conditions were met and whatnot. Okay. So you can imagine this is a hypothetical conversation between a Bayesian and a frequentist. The Bayesian would just go and ask, say, why don't you just estimate, say, directly what's the probability of theta greater than 0 or probability of particular hypothesis given the data? And as a frequentist response is the question is meaningless because theta by themselves is fixed and cannot vary. And then the Bayesian says, then what do you do? This is how frequentist response, and that's in fact how most statistics is being practiced. You calculate the probability of a test statistics that's based on the data. It's in a rejection region given the hypothesis is true. Okay. In a way, that's what it does. But the Bayesian say, well, isn't the data already being collected and known? Meaning that you see 17 observations, you don't see any more since you haven't seen them. The frequentist response be, we will see an infinite amount of similar data in the future. And when the analysis is repeated thousands of times, this is again coming down the foundation of frequentist definition of probability in repeating a frequency will be right at 95% of the time. This is what referred to be a coverage probability. That is in fact correct. Okay, but the Bayesian's perspective is, well, what do you say about the current analysis given the data that you have to have? That ideologically frequentists don't have any statement about because it's not about a particular experiment that one has seen. It is what would happen if we were to repeat it many, many times. And often a criticism of on the Bayesian is the prior distribution is garbage, which in a way, many times is probably also true. So I just want to use this hypothetical conversation to illustrate how two sides of the camp think about things. And it's fair to say that there are two major criticisms on the Bayesian paradigm. The first criticism is, should a parameter be fixed or random? The response is, whether a parameter is fixed or random is rather a moot point because we don't know. What we truly are concerned about is we still have this uncertainty about the true value, having about the parameter and having a distribution to describe the uncertainty about a parameter has many benefits in that sense. And the second criticism is whether the prior distribution contains too much this thing called subject information, meaning that you form your opinion too strongly in the analysis. The Bayesian response is, well, scientific inquiries themselves are subjective to begin with. It is a fact that we don't look at the same data and reach same conclusion. If we were to do that, then people will not argue and dispute in general. And the Bayesian paradigm simply reflects this general scientific inquiry, how it works, rely on each individual bring their own opinions and knowledge in the process. And we are just being honest about when we updating information from the prior to the posterior, we simply mean when facts change, we change our mind. I change my mind. That came from the expression of the Kim, is expressing the thoughts that you combine your prior information and the knowledge, you get your posterior. And on the other side, much of the statistical modeling themselves, when we talk about subjective, is very much subjective. The choice of likelihood function, the selection or the choice of p-value equal to 0.5 and all that. So the very much desire to criticize because something is subjective, therefore it's bad, typically isn't as valid. Okay, I'm just watching my time. I'm trying to do 20 minutes for the Bayesian and 20 minutes for the software. I think I'm doing all right. So I'm just doing a simple example to illustrate it. Suppose that in connection of the data, you see 14 heads in 17 tosses. You have a likelihood function, and the likelihood function is a function about your x. So that's a random variable, is x. And then now you have a flat prior. The prior just as my prior is 1, that means I express my equal preference on p, the possible value of p, and I say it's as likely between 0 and 1. Okay, and then the posterior is you multiply 2 and 2 together, you get this posterior functional has the same form as what is here, except the random variable now instead of as x, which makes a binomial, it becomes p, which makes it a beta distribution. And so you can plot it. And so in the binomial, the posterior distribution is identical to the likelihood function if a flat prior is used. Okay, so that's what it is. It doesn't change the shape of the posterior distribution. And now you ask the question, if the likelihood function and the posterior are identical, do we get the same inference, same answer? The answer is no. So here we just zoom in the concentrated area here in this region. Okay, so there are two curves. The black curve is the likelihood or the posterior distribution, and then this point is the mode, and then the red curve are normal approximation. So the classical inference typically use asymptotic result. You hill climb to the top, that's your MLE, and the curvature around it came from asymptotics, meaning what? Meaning that if you were to see more and more data, you know this shape would behave more and more like normal. And then you go to the asymptotic and you come back and you plug in the number of a normal approximation, and that's what you use for confidence interval and such. The Bayesian inference is completely based on this distribution, which has, doesn't have any nice, not guaranteed to have nice shape. It just has a distribution as what it is. Okay. So in a sense, the key point that I want to get across is that you always have to defend something. Everybody is slave to the likelihood function. That is the foundation of both paradigm. This is what the data is. And given that in Bayesian paradigm, you need to justify the selection of your prior. In classical paradigm, I think you need to justify a more difficult assumption, is you need to justify the asymptotics. That there exists an infinite amount of unobserved data that are just like the one you have seen. You just haven't seen it. But if you will have more time to see it, you will see more and more. If that assumption holds true, then the inference is very much valid on that sense. Okay. So that is my 15 minutes introduction to Bayesian paradigm. Now we're going to talk about the technique which we use. And now the focus of the technique is estimating this distribution. Okay, because Well, Bayesian uses this distribution to capture all inference. Once you have estimate this distribution, it almost boils down to the end game. That's all, or you do all you need to do. You can make all inferences based on that posterior distribution. Okay. So there are two parts, simulation and approximation for it. So the goal is to estimate this thing, okay, which you need to be accurate because this is the basis of all Bayesian inference. Once you estimate it, there's a second task is you got to find point estimates to describe something, describe what's my most likely value that I represent, like the MLE, and people typically use expected value of the expected of posterior, expect value of your theta with respect to posterior distribution. So there are two tasks that's involved in here. For the past decades, 3 or 4 decades at this point, the most popular methods for estimating this distribution is sampling based, is using MCMC. And the nice thing about MCMC is once you use simulation to draw a sample from a target distribution, the second task, this task, is actually trivial. This is called Monte Carlo. And Monte Carlo, in fact, is just integral. It boils down to the summation of the integrals. So that just means that if you are able to draw sample from a target distribution, you plug in the sample or many times over, you can solve the second problem fairly easily. And now the dimension of the theta doesn't impact the accuracy of Monte Carlo estimate. That's the thing. So now we are talking about simulation-based estimation. What's the idea of simulation is if you know the true density is the dark line, the black line, and if you can sample, what does it mean? Sample just means sample by proportion. Okay, so under it's sample by under the curve. How frequent that you want your sample should fall under depends on how likely that you are in that region. If you can do that, you can get a very accurate estimate, which is a red line in there. Okay, so there are two obstacles. If the distribution is arbitrary, and you have unknown normalizing constant, because you got to have a distribution, you got to deal with this piece. And then the second is the dimension of theta is very high. So it just makes things much more difficult. This difficulty of high dimensional or unable to generate from a non-standard arbitrary distribution is solved by Ulmer and Metropolis. What they essentially said is instead of sampling directly from that distribution, so if your target distribution is a normal distribution, you can have a normal random number generator function to generate from it. If they say you don't need to do that, they say if you can somehow generate from a Markov chain and the stationary distribution is that thing, you get what you want. Okay, so that's why Markov chain came about. And then the Gibbs and the Metropolis changed the landscape of simulation based computation. All right, so the difficulty is the genius is to say you can construct a Markov chain that's having nothing to do with directly sample from a distribution, but you ended up getting what you want to get. They certainly didn't tell you how to do it, and that's where the Gibbs sampler comes in. So Gibbs sampler just says if I have a parameter space is too big, like in the thousands of theta, Gelman in 84 paper says you can break them into much smaller dimension and still get what you want. So the collection of the sample, that means that you will still get the joint sample from a high dimensional problem. And they also show that conditional distribution can jointly determine a unique joint distribution. That's where and they coined the name Gibbs. And I think many people knows what Gibbs means, and it's just a very 30 seconds slide to show it. If you want to do a joint distribution, it's too hard, high dimensional, you break it down to a smaller dimension, which condition on some of the parameter, and you sample from this, and then you continue doing many of these called conditional sampling. By the end of the day, your sample are from this joint distribution. So the contribution of Gibbs sampler is that it breaks the high dimensional problem into low dimensional pieces that they said, if you could do that, you are fine, okay? but it doesn't tell you how to sample from an arbitrary low dimensional problem. And that comes with, you require these general black box algorithm that can guarantee this property called sampling by proportion. And the Metropolis is one of them. Okay, so we move on to Metropolis. And the Metropolis story is the following. The Metropolis only requires two basic ingredients, which are easy to get. One is a numerical evaluation of the target distribution, and you don't need to get a requirement on a normalizing constant. Okay. And the second thing is a simple random number generator. It's a normal and a uniform or whatnot. So you get two of these pieces, you are guaranteed to be able to sample from any arbitrary distribution. Okay. So this is the picture that I want to show. Let's just imagine this is a distribution that is we are interested in sampling from. Okay, and we start somewhere and call it theta 0. What Metropolis says that I'm center my theta 0, and I'm just going to use a random number generator function, a normal, centered at where I am, and has some steps. Okay, I'm just taking some random step around me, and I'm going to take one step, and I'm going to get theta star to theta prime. And then now I'm just going to evaluate the two density, the height. So that's why it's important to have this piece, the numerical evaluation of this piece, and a random number generator. Once you do that, you don't need to know anything about this distribution. You don't need to know if it's a normal, a mixture of normal, or inverse gamma. You do that. And the rule is, if the new density is higher than where you are, you always move. Okay, your Markov chain move from one value to the other. This is what Markov chain means. Markov chain means where you will be depends on where you were. Okay, so they are not independent samples. They are conditioned samples. Okay, so the rule is if you're high, you always move. But if you were low, you accept with the probability of this height over this height. In other words, and then you repeat. Once you accept, you repeat. So in other words, the Markov chain always moves to areas that have a higher density, but it still explores the tail density with tail area with low density area. So it enables to a Markov chain to traverse the entire parameter space. How often it mostly comes here because the density is high, and it sometimes would have to go to the tail and with corresponding probability. And you don't need to know anything about this this distribution. So you can look at, this is called a trace plot of, if you have a target distribution now, just say normal 0, 1, and you start at some places really far, it will gradually go to where the high density area is, and it will stay where it is. So this is iteration, and I'm just connecting the line of the iteration of the trace plot, and it will stay mostly where 0 is, but it will go to the tail and come back, and go to the tail and come back. And then you'll be able to estimate this distribution. If you do that many times in as many as you want, you can estimate this distribution to any degree of accuracy. So the question is the disadvantage and a disadvantage of the Metropolis algorithm. Is the pro is you really need to have minimum requirement. As long as you can numerically estimate something or compute something, you can do it. You can do it for a very complex model, and it's very easy to implement, and it's very robust. But the cons is relatively slow. That just means that it doesn't traverse a parameter space very efficiently. And in that sense, just means how big of a step that it takes, whether they should take always the same step in all of the parameter space, and things gets to be high dimension, gets to be tricky. So that's tells to be the relatively slow comments on what Metropolis sampling algorithm refers to. Okay. So next, we are going to talk about a recent development called Hamiltonian Monte Carlo. So we have now we see the problem of Metropolis of the MCMC, the high dimensional MCMC, Gibbs break down the problem into smaller dimension, and there's many general algorithm. Metropolis is one of them to enable sampling a black box operation from low dimensional problem, and that's the gist of most of the MCMC based algorithm is. And Hamiltonian Monte Carlo is slightly different. It is still Markov chain, but it doesn't do things on piecemeal. It does the whole thing in one shot, okay? And that's how I'm going to explain how that works. So two pieces of the puzzle, the parameter, and then Hamiltonian Monte Carlo also invented this thing called auxiliary momentum variable, and I'll explain what they are. And the key of it is maintaining Hamiltonian dynamics. Once you're maintaining this thing called Hamiltonian dynamics, you can jump very, very far. Like Metropolis, where you are dictate where you will be because of the normal proposal. So you are exploring locally, but Hamiltonian Monte Carlo promise that you'll be able to jump things very far from where you are, okay? So if without going to the detail, this is not too difficult to understand. You have parameter of theta. Let's say that parameter theta is 5,000, okay? You're going to introduce a momentum variable called R. That is on the same dimension of theta. So you essentially double your parameter space by two, by double, 5,000 to 10,000. Okay? And two of them result into a joint distribution of theta and R. Just means that you have two random variables together to be the same thing. And you express them into such a way of this piece is log likelihood from the posterior, this piece from the normal. So the basic ingredients of the joint distribution isn't too hard. You know, you can visualize it. It's just that you have a posterior distribution and you have a normal kernel. So from a physics perspective, 2 and 2 add together form a Hamiltonian dynamic Monte Carlo. You can think about theta as position and R as momentum. So this piece is a potential energy and this piece is kinetic energy. 2 and 2 add together, and by physics law, they gotta be constant. Okay, it is kind of magical, but that's just how the idea of physics came into help with sampling. So visualizing it, this is how we see it. You have theta. Okay, and consider this is your distribution on the log scale, and you have theta 0, and this piece is your position and give you potential energy. All right, and then this is a U theta, and then you have your R0, and you get your kinetic energy. 2 and 2 together kind of form a Hamiltonian equilibrium. So essentially it says that if you move along this line anywhere, you'll be able to you maintain this Hamiltonian dynamics. In the 2 dimension, they form a contour, okay? And Hamiltonian Monte Carlo just means that you have a technique called leapfrog. Don't worry about what that means. That you jump along this curve, this contour. As long as you jump, you can get there. You get what you want. Okay, this is efficiency jumping in here. So once you do from theta 0, you jump to a new place called theta star. You repeat the same thing by evaluating this amount of potential energy and the kinetic energy. This piece is also random, form a different contour. Then you repeat the exercise that enable you to explore the parameter space of theta much more efficiently. Okay, then you just leapfrog. This is the thing. All right. So, but of course, how you do it involves a bit more tricky things, and how you maintain this piece, and how to do that, and it involves derivatives and whatnot. But this is the basic and general ideas of it. Okay, and you can see the results of it is that Hamiltonian Monte Carlo can traverse a distribution more quickly than a metropolis. Metropolis though slow, that asymptotically this is still valid. It's just that the mixing capability, that where I am to where I will be, are more or less independent. Just means you do that. You can traverse the parameter space using a fewer number of samples. Okay. Like all things, there are the pros and cons, and HMC does lead to rapid convergence, but it depends on, in the leapfrog, the step size and how many steps you take. Okay, so there comes this Hoffman and Gelman paper that proposed they called a no U-turn sampler to automatically tune epsilon and L, and this is being used in a number of software packages to deal with the problem. And the one drawback of HMC is it is computationally intensive, in the sense that you literally doing 5,000 dimension jump at one time, and in order to do that, you have to do a lot of derivative computation and whatnot. Just imagine that, and you can't just do a single step, and this typically is many different steps. So it's computationally intensive. All right, so let's talk about the benefits of sampling-based methods, and why people have been on a binge of MCMC for the past almost 30 years. Simulation-based methods can get very accurate estimation of the posterior, although they tend to be slow or computationally intensive. They get what you want. But a more important question is, in order for you to inference, you want a marginal distribution. Okay, what that means is that you want to know what the distribution of my parameter of interest is without having to know any other parameters. Okay, so typically in a linear regression, you have your fixed parameters, you have your variance, you have whatnot, and all you care is what my posterior distribution of sigma yi, and this says I need to integrate out the parameter or any other parameters in this distribution. I gotta get rid of them. I need to, in other words, I need to propagate the uncertainty of this distribution into the marginal distribution in here. This is a numerical problem. This is not as easy to do because it's a high dimensional problem. Like if you have a 5,000 dimension, you got to do 4,000 dimension integral. And then numerically, this is daunting. Okay, and that's why sampling comes in, and it comes very handy. What MCMC or Gibbs enable you to do from a joint distribution? Okay, and you can do it in Hamiltonian. It doesn't matter. So what joint distribution says is that these two samples, they came in pair. They came as you would see as a high dimensional problem. And now you throw away the betas. It's just as simple as you throw away what you don't want to have. You keep what you want to have. This is a marginal distribution. Okay, this simplicity just means that when you essentially just says when you do this marginal computationally, you get this marginal distribution for free. All right, and this essentially is what saved Bayesian, because if you got to do a imagine you have a high dimensional problem of 5,000 dimension. You just don't worry about the 4,999 dimension. You keep what you want to do, as long as you design a Markov chain that guaranteed sample from the 5,000 dimensional space. Okay, and you do the same thing. If you want to know what the beta is, and you just draw from the beta. This enable you to make inference on any marginal distribution. And additional immediate convenience of MCMC is that you can estimate the functions of parameters, any functions of parameters directly. So for example, if you want to know the difference in treatment effects, okay, what to do? If you have, say, treatment effects from one group or the other, is alpha hat and beta hat, in classical statistics, what do? You plug them in. You plug the MLE. And then how do you quantify the uncertainty? you do central limit theorem, you do Taylor expansion, and you do delta methods to compute the standard error. And if this function gets to be complicated, you got to be pretty creative in do what you need to do to figure out the tail of the delta methods go down in the ways that you want it. But for MCMC, you use plugin method for every sample, and you get what you want. And so if you have alpha and beta, imagine any parameter that you want to know, any function, you plug them in, you just compute this pairwise, and you get a posterior distribution. And from this posterior distribution, you can make any inference you want. You can compute the probability of alpha minus beta is greater than 1 but less than 5. You just count. And so to Bayesian from MCMC, that's why people like MCMC, is that once you get the sample from the joint distribution, there's nothing you need to worry about. You do all these inference afterwards. It's almost for free. Okay. I am running, it's 12:38, so I will be quick to talk about some approximation methods. That's more widely used outside of the statistics, and now more and more people are in statistics are using it. And then the approximation methods are one of the important aspects of technique that estimate the posterior distribution, and the trade-off is speed. Okay. Because MCMC, by the end of the day, Hamiltonian is still too slow. Okay. So the idea is to find a surrogate distribution that find to be the best approximation to the true function of what you want. Okay. And once you have a surrogate distribution, you'll be able to find the expected value of surrogate distribution. This, of course, it's not convenient in MCMC, but hopefully if the surrogate distribution is manageable, this piece is computable. And there's three pieces: Laplace, variational, and expectation. Laplace is just asymptotic. I think most people understand what Laplace is. You go to the mode and you do the curvature and use a normal approximation to approximate the posterior distribution. It has its pros and cons. I'm not gonna go. I think most people understand what Laplace approximation is. And I will talk about variational base and expectation propagation. These are kind of interesting cases. In Laplace approximation, the surrogate density is normal. Okay, but that's not the only thing you can have. You can try to find a distribution that is close to the density through some divergence criteria, and often people use this Kullback-Leibniz distance. Okay, so that's this P and the Q, and I want to be going slow on here so that people understand what this thing is. And I think most people don't deal with Kullback-Leibniz divergence very often. You want to have a target distribution. You want to find a Q that's approximated is best case. You essentially looking for the expected value of the ratio with respect to the posterior with target distribution. So this piece must be the target distribution. All right. Okay. So let's say when the P0 is pi of posterior, you essentially want to find approximating distribution of Q that minimizes this distance, the expected ratio difference with respect to here. Okay. Except this is very difficult to do. I mean, you can't, this is a posterior distribution. How are you going to find a thing that minimizes this distance in here? Okay, this is just very difficult to do. So Michael Jordan from Berkeley came up with a solution. Is he literally flipped P and Q. Okay, he said, I can't do this piece. I know that I want to do, I can't. So I'm going to flip them, and I'm going to find the Kullback-Leibniz distance between minimize Q and P. All right. And if you are a statistician, you know this is something fundamentally not quite right, because you want to find a approximated distribution to something real, but you can't. And you say, I am going to limit myself to a subclass of the distribution I can work with and find the ones that can minimize this quantity. So you're finding the best of the class that I have to approximate what I would want to approximate. And so that means you have the family approximating the density of Q, and you find the best bunch in the Q star. That's a fundamental idea of variational inference. It also changed the integral problem into a optimization problem. And the method is widely used in machine learning and science. So credit goes to Michael Jordan. And then there is this many articles written on it. But I would recommend you read the 27 paper, Variation Inference, a Review for Statistician, to see how variation inference to do with statistics. All right. So the only thing I want to go through is at this point is you got to come up with a predetermined covariational family of Q, and the key people doing now is a mean field variational field. They just said, I'm going to treat everything as independent. All right. And you got this picture. If the exact posterior is this, the mean field approximation is right here. Okay. It certainly doesn't approximate the correlation. It underestimates the standard deviation. From a statistical perspective, a lot of things is wrong, but it get the mode right, it get the estimation right. Okay, and if you do a lot of problems that estimation prediction is what you want to use variational methods because it's fast. It really is fast. It breaks down a problem into, of course, how to make it fast is a different story. I'm not trying to show all this. But from a statistical inference perspective, it certainly underestimates the standard deviation and the variance. That's a known problem for it. Now we come to the expectation propagation. Okay, expectation propagation deal with minimizing Kullback-Leibniz distance in the right way. So they say, Tom Minka said, I still want to minimize this. I don't want to flip them. I want to minimize this Kullback-Leibniz distance with respect to the P of theta. And the observation is, in a Bayesian problem, I always have the joint posterior can be break down to smaller pieces. Think of just likelihood for one piece. Okay, so that's a futuristic thing. Now, if I can find a high dimensional problem that can be a product of smaller pieces, and if each of the small piece can approximate a piece of the likelihood, we probably can find a simple approximation. Okay, so he's saying that I am breaking down to a larger problem into smaller pieces, and each small piece represents a likelihood piece and a prior in some case. Okay, so think of it this way: you have n observations, you have n piece of the likelihood, and if I can find a function to approximate each piece, then maybe I'm done. Okay, this idea is not entirely new, except it's very difficult to do. Okay, you want to minimize these two pieces. You want to find the expected value of the posterior of this piece to minimize it. That's impossible. So what helps is to have this P star tilde to be in the exponential family distribution. And this is a well-known fact, is that if you choose your exponential family distribution as a surrogate distribution, you can minimize this by matching the moments of the sufficient statistic. Okay, this is magical. This is magical. So what other words is that if you choose exponential family distribution and you know what your sufficient statistics, you match the expect sufficient statistics can minimize the KL divergence. If you choose your P tilde to be normal, all you need to do is to match the mean and the variance terms. Okay. All right, so just the main idea behind it is to minimize these two things is too difficult. Let's do one at a time. And if I can do one at a time, we do anything, then this piece would work. Except if you do this one piece and a piece at a time, it's horrible. This is a horrible approximation. Okay. Tom Minga's contribution is to find a way to say, I am using everybody else to help me to approximate this piece. This is called message, it's propagation. That's where the idea of propagation comes from. Messaging passing in propagation is for any of these little pieces, I'm utilizing everybody else that I haven't touched to help me improve this thing. And it works remarkably well. And the thing is very, very simple. It repeats itself. Of course, how you actually make the thing to match in the moments gets to be tricky. But it's a drastic improvement over the existing idea of KL. So this is a Tom Minga 2000 thesis to demonstrate the badly shape of one-dimensional approximation of theta p tilde versus if you use everyone else's information to come to help you, and you get much, much better. Okay. So that's the and so variational based and variational based and expectation propagation are two high dimensional. They really solve very high dimensional problem, and then they can it's fast and individual pieces are easy to deal with, and that's often the case whenever you deal with machine learning tool. Whenever deal with large dimensional neural network type of thing, each individual piece are cheap to do, and you use these approximation methods to do it, and they can do it fast. Okay? So because there are certain drawbacks for every methods here and there, but that's not quite the case. All right, so I'm going to spend the last 11 minutes to go through the software of what's being used in the field nowadays of survey. Majority of current day Bayesian software is sampling based, still heavily rely on MCMC. And you just give me an arbitrary prior likelihood function and hierarchical. I'm going to generate a sample of pi of theta that generates here. And for non-traditional statistics community, like in computer science and machine learning, approximation methods are much more widely adopted, not adopted. So again, I want to point out that typically there are different type of problems that we're trying to solve. Modeling is one thing. In computer science, machine learning prediction is more of a driven. So point estimates is more important in quantifying uncertainty. But quantifying uncertainty is much more important from a statistical perspective. And they're merging, but still, they're different. So simulation, there are many open source software. One noticeably is bugs, and there are inference JAGs and Nimbus, and then you have Stan, and if you are Python, you have PyMC, MC3. From a commercial software, SAS has PROC MCMC, Stata has their own software, and these are simulation based. And approximation based is info.net, is Tom Minga's Microsoft Research Lab, uses expectation propagation. And there's a gazillion number of variational based. And you can also have integrated and nested across approximation called INLA. So these are approximation based things here. I think this is more or less, I'm just really, because I'm running short on time, I'm just giving people a general idea of what a general Bayesian software to do. The basic components of general Bayesian software is this thing called probabilistic programming language. That just you define relationship between variables. Parameter, random variable, need to have a distribution, data need to have a distribution, and you got to have programming capability to say, mu is a function of something else. I call this deterministic. This is a probability. Any software probabilistic programming language have these two pieces in it. So the bugs project, Bayesian using Bayesian inference using Gibbs sampling, it would just code look like this. Okay, there's a lot of indexing of y and the beta and the pi distribution. And then it has a compiled machine that deal with sampling problem. The readability is a thing, because for a statistician to work, you want to be able to write what you write down and connect with what you have here. And when bugs from the 90s, early 90s, it was the first software to do that. And then it led to the development of a bunch of bugs related projects, win bugs, open bugs, multi bugs, and influenced the software like the development of JAX and Nimble. I am not going to go through what WinBugs does. It's a window version of bugs. JAX extended on the WinBugs philosophy, except it made it more portable on different machine. You can give it more freedom because bugs is just a black box operator. You can write your own function, distribution, and sampler, and so on. That's what JAX does. And that very version of WinBugs, they stopped supporting it. They stopped supporting in 2007. It led to open bugs, but they haven't been supporting very much. And the recent, they started again, it's called multi-bug. Multi-bugs is just a multi-parallel version of the bugs. Seeing it. Once you know how to use bugs, you transition to any of these software is very easy. One thing that you want to think about when you think about these software is the standalone feature. The bugs package, or the many other software package, because they are not embedded in a particular programming language, they are separate. So they are separate from your interface language. So they essentially have to store everything in the memory that they have. Such as input data set and posterior samples, which can be crucial in some situations because they are not part of the native language to see. And the second is any bugs and the bugs inspired software, you have to know visualize the entire thing. Okay, that just means you have to do a lot of indexing. You say, well, what is I, what is the J? Every nodes need to count because they form a directed acyclic model. Typically, it's not a problem. It gives flexibility because you get random access to many things. You can do a lot of things. But the downside is you actually have to count all the time, even for a very simple model. And there's a lot of counting. There's a lot of counting. Even you fit a simple linear regression, you got to count. You got to know how many hospitals you have, how many matches you have with doctors and whatnot. The Nimble is, if you think about WinBugs, is a standalone software package, which is a very black box-ish thing. You can't modify much of it. And what people do is they use the interface language, often is the R, and then they send a program to bugs and they collect the results back. Okay. And now Nimble did something different. They made the software closer to R, want to be more deeply embedded with the R language. Right. They not only give you more customization capability to say you want to change your sampler, can incorporate your own sampler to be part of the software. You can actually write code in R, and the software parse it and translate into C++, compile and execute. And you can imagine how daunting this project is. And that's why they only support a subset of R. R is an interpreted language. It's not like, it's not a compiled language for that shit. So you can't do arbitrary R function in Nimble. And so in Nimble, you have two pieces. In model specification, they stick with the WinBugs. And in functional definition, they have a bunch of limited R functions that you can do in that define. If you're not using R programmer, it doesn't make sense. But if you do, you can see a lot of pieces here are really in the R. Okay. So in general, a software, if it's embedded in a high-level programming, you can count on calling arbitrary function in their language. But if it's not, you cannot. But Nimble is being actively developed. Its source is written in C++, and I think it's more accessible and extendable than the component Pascal that's using from bugs. PROC MCMC is what SAS has. It's also a general sampling general purpose sampling procedure in STAT. The procedure is not graphical model based. The model is specified relying on the usage of symbols, not array and array indices. So it's more like a C-like thing. It follows the idea of data step. So it's essentially embedded data step functionality in a procedure and build a probabilistic programming language inside the MCMC procedure. Okay. So it supports what you would expect to support, standard math function. You can specify your own distribution, function in algorithm, and it has a large class of MCMC algorithm, Metropolis to Hamiltonian Monte Carlo. Traditionally, in the SAS land, you use statement to tell procedure something, and that is what SAS user would expect. So prior tell the procedure the alpha, the prior distribution, the model inform the likelihood. And instead of explicitly indexing the for loop of I through j, the procedure does an implicit looping through the input data set behind the scene. Okay, this is a traditional SAS feature of it. So these are differences. And then and because it's native in SAS, it can do a lot of behind the scene internal processing, such as handling subject variable in random, building up the random effect models, so on. So if you live in a SAS environment, PROC MCMC will be your choice in doing Bayesian modeling and exploration. You can utilize this data step, graphics, and other procedure or not in that sense. I am 2 minutes. Okay, I am finishing up maybe with Stan and the Python. So Stan is named after Ulma. I don't know how to pronounce Ulma. Stanley Ulma, pioneer of the Monte Carlo methods. Came out of Gelman's group in Columbia. It doesn't do Gibbs. Okay, it also moved away from Gibbs-like model specification, and it's like a C-like programming language in that sense. It's in the same idea as like MCMC in a C-like. Yes, you have to use semicolon just so that people who are used to using R, you have to use semicolon. Okay, so it doesn't assign any sampling scheme. It does only one thing. It does Hamiltonian Monte Carlo. It does no U-turn sampling algorithm. And it requires functional evaluation derivatives. So a script language environment is sufficient. That's why it's C-like. That's all the thing. And has three parts. And you have data part, parameter part, and the model part. And data part is what, if you program in C, this is very familiar in that sense. You have your data part, and you declare your parameter, and has a lot of different options you can do, and you specify the model, and it goes about and deploys a nuts algorithm that do it. Yeah, Stan is compiled in C++ and doing it in Python. Susan, it's 1 o'clock, so I want to be on time. Do you want me to stop, or you want me to keep going? I mean, I think people can, if people have any questions, I'd be happy to answer some of the questions, or I can just keep going. And I have about a few more slides, and I finish and then be end of it.
I'll leave it up to you, or if people want to text into what they want to do, that's I'm flexible.
Okay, I don't want to hold people. We tend to try to stay on time. I actually finished 105 slides out of 116, so it's not too bad. I'm just going to keep going. It just be a few more minutes. And if people want to stay, you can stay. And if you want to send me a comment, I can't see anyone actually had sent me any notes. So I assume that they probably are. Nobody has. Okay.
Yeah, I think you're good.
Okay, I'm good. Okay. And then Python. Python, they have their own general thing. When it comes to software drives applications, I think interface language often becomes relevant. And if you use Python, then your choice should be Python-based Bayesian software as in Python MC3. Okay, it is a probabilistic programming language, but it doesn't look familiar to a statistician. But if you're a Python user, this probably is a non-issue. It looks like something like this. To specify a generalized linear hierarchical model in here, you can pick out the pieces. I think it's just syntax. You have to know what it does, and it has these, building prior is equal to prior. You might have to specify multiple things at multiple places. You have to say prior is here, and then you have to pass the prior into here. It's a Python language, and it is Python MC3 is based on HMC. It requires derivatives, nuts, and symbolic differentiation. It builds on Theano. So because it's native to Python, everything is easy. Your distribution functions, as long as they're defined on Theona, then you're good with it. I want to spend the last 2-3 minutes to talk about some features and comparison. Overall, these software packages all have the same objective, the generality and the flexibility. The actual development offers discrepancy. I think by the end of the day, they will all merge to somewhere similar because of the following reason. So to any Bayesian software package, two basic components are here. One is a sampling algorithm, which we know have a limited set. We know what they are: Metropolis, Gibbs, conjugate, Hamiltonian, approximation methods, and it's a question of implementation. So as long as they're adding to it, they will eventually get there. And the second is compiler and the hardware issue is boils down to how fast you can evaluate a single likelihood function. And that's why everyone uses compiler and everyone runs on the same Intel machine. And so the second issue is really not a software issue. The general package came down to the selection of sampling algorithm. So because currently everybody does things slightly different, you can make general comparison on efficiency and stability. But I think that comparison largely reflects on the choice of sampling algorithm. You are really comparing conjugate sampler versus Metropolis, Gibbs versus Hamiltonian Monte Carlo. And therefore, you can always find a situation that one software package outperforms others. So of course, everybody has their own uniqueness. Some software doesn't support if else. Some software like Stan doesn't support discrete parameter. You can't do categorical, so you got to be clever about how to do things. But there's always ways that you can do it. How to deal with missing data it doesn't handle correctly, or I'm not sorry, it just doesn't handle. It doesn't like it. You got to have fun way to do it. But I think all of these can be overcome with tricks, better understanding, different formulation, and since everyone is still developing them, I think they will. Everybody will get better in that sense. There are some shared deficiency I want to point out. Most packages only work numerical continuous or integer variable. So that means most software, all of them, don't have this thing called class statement. That you have a categorical variable and you want to fit that into a regression, none of the software does it. The reason is a general software package requires a complete specification of a model. That you have to know what prior, how many beta, if a class variable, class male, class female that you have, and what prior they have. Because these beta parameters can enter the model in any linear, nonlinear way. I mean, there's no way you can have a work for all prior distribution. So you must know in advance how many beta parameters there are before assigning prior distribution and such. And because of this deficiency, all these software punt the problem to the user. Okay, now this becomes a user issue. And in R, you use model.matrix to figure out a design matrix, and in SAS, you use PROC transreg to do it. And it is not ideal. It is not. I work for SAS and I do PROC MCMC. I'm the first one to acknowledge that this is not an ideal situation, because if you were to repeat your model on data that have changing dimension, same model, but one variable of interaction between A and B. A in some variable hospital has 17 hospital, other has 278 hospital. Then it becomes very tricky to how to use it. Okay, so that is the thing. And another thing is interface software is often drives the use of individual Bayesian software package as they see now. So all user JAG, Nimble, Stan, SAS use PROC MCMC, Python use PyMC3. And the user are given the modeling flexibility, but you got to be ready to program. Okay, so that's the thing. And the more code you write, the more likely you are to make mistakes. And customizing code is also difficult to maintain. And here, just an example. This is like doing a meta network analysis or using Winbugs. You look at the code, sometimes you go, well, I don't know if it even works. And there could be many places in here that you can potentially make mistakes. So some finishing thoughts is, as we see more need for Bayesian software packages, I think we need to see more specialized tool for it. And of course, in R, people are writing different packages. So in SAS, we have PROC BGLIM that does Bayesian generalized linear mixed effects model, PROC BChoice that does a Bayesian discrete choice model that simplifies the burden on the programming, but dealing with a larger class of models that's flexible and can handle many situations. And I just, this is a comment on the software packages in R seem to scatter around. Like when people, a user, when start to use it, they aren't quite sure what software package or what library they should use. For linear model, should based on LM or BLR or Bayes regress. I think it was simplified if the math library in R came out with one simple function to use, like the LM function, and then people, and this is a way to sort of promote that. And then I'm finishing with a discussion point. I know it's not a discussion point, but is promoting research-focused software package, like MCMC, Nimble, all that. The focus is if you can assemble the pieces, the software will get you what you want. And the way to promote Bayesian paradigm, whether it's the right way or most efficient way of doing it, at SAS, we think we should do it in two fronts. One is building these tools that people can use. One is enhancing these general Bayesian software packages. So speaking of that, this is it. So this is the end of my my talk. And if people have any questions or comments, they'd like to get in touch, this is my email. The essential Bayes paradigm technique and software was part of a continuing education CE course I taught at JSM that went on for a whole day. But that has paradigm technique, software, and applications. So this is a very condensed version of it. And I hope I was not being too rushed to do so within an hour and 8 minutes. So thank you all for tuning in. And